Hi friends, this is the second lecture of missions. In this lecture we will learn about the equivalent circuit of the transformer, circuit of transformer, second one impedance reference, referring the reference, third one some part of hysteresis losses. Okay, this is all we will cover in this lecture. So some practice problems will be there, two practice problems. Okay, first one. Yesterday in previous class we have left the phasor diagram of the ideal transformer under loaded conditions. So this is done here. See here, first one we'll take phi as reference, phi, then V1 applied voltage. Okay, so this is V1. V1 is equal to minus E1. Next, this is E1. This is E2 is equal to V2. Here, since leakage impedance is equal to 0. D2 is equal to 0. That's why E2 is equal to V2. Here we'll get a lagging load, that is lagging current I2. Then I2 dash will be referred to the primary side. Then this is IE. The phasor sum of IE and I2 dash will give I1. This is all phasor diagram of transformer under loaded condition in considering ideal transformer. Okay, now we will go to introduce the non-linearities or non-idealities of the transformer one by one. Here, first one we have assumed that the core loss in the transformer is equal to 0. PC is not equal to 0 for practical transformer. How? So in a practical transformer, there are two losses. One is eddy current loss and other one is hysteresis losses. So these two losses are met by the primary voltage source. So in addition to the eddy current, we have taken a power from the primary source. That is, these two losses are met by the primary voltage source. So here we have assumed that IE is 90 degrees lagging. So no active power loss in ideal transformer. But in practical, IE not at 90 degrees to V1. So we have assumed that here, see, this is V1, this is phi, this is IE. This is, so here 190 degrees phase displacement is there, 90 degrees. So active power P active is equal to V1 I1 cos phi, that is equal to V1 I1 cos 90, that is equal to 0. This is in ideal conditions. But in practical condition, this IE is not in phase with phi. This is some angle deviation will be there. Thus, this angle is called hysteresis angle. This angle is called hysteresis angle. How it will come? So it can be justified by using the BH curve or hysteresis loop. See how it is. So I am drawing a time phasor diagram here. This is I. So this is lagging. So phi is lagging at an angle of phi, at an angle of alpha. This is phi. Phi is greater than I. Okay. This is hysteresis angle alpha. Okay. I E. This is I comma phi. This is T. So coming to phasor BH curve of a core. See, this is initially, then there will be deviation of the path, and this is the normal BH loop of a curve, the BH loop of a core. This is H we will take normally, this is B we will take normally. This is peak point. Initially the flux is the current, this curve, this path is maintained here, and then it will goes to in this path. This is hysteresis loop, of course. Now take this figure and comparison to this figure. So normally H is equal to MMF, is it? So that is equal to N into I. Can I? So N is constant, so H is directly proportional to I. So we can write I also here. Here, so B is equal to flux per area. So I can write A is constant, so we can write phi here. So analogy taken here. So first one, I have taken I0, first point here, I0, and at the time of I0 there is a small part of the phi at negative value. This is, so phi negative. So negative phi will be appeared here. See here, this is negative value of phi. Negative value of phi. This part. And now move. I is increases. Here is I increases. Move to the right. So phi value decreases. So phi value decreases. Come to 0 at the point of some I value. This is that I value. So here phi is equal to 0, but I not equal to 0. See here, this phi is equal to 0, but I value is positive I. And now increase the I value, and then again we'll get positive value of phi. This is positive value of phi. So at the value of peak current, this peak current, then even though you increase the I value, there is no increase in the flux value. This is called saturation point. Saturation point. Now this. So now we'll decrease the current from this point to, we will decrease here, decreasing current. So we'll come to back in this path. But phi does not follow the same path, but it follows the other path because of dipoles, already existing dipoles present in the core. That movement doesn't change instantaneously. That's why there will be some deviation in the path of the flux. That deviation is taken in this way. So here, we will decrease the current, so at the time of current 0, there will be a positive flux. So this is, see here, this is current 0, I is equal to 0 here, but the flux is positive. This amount of flux is phi is positive. So there is a entire similarity between this figure, this loop and this loop. We can conclude that IE is leading phi by an angle alpha called hysteresis angle. This angle. From this, we'll say that we'll write the phasor diagram at the no load condition. That is, I is in this way. This is alpha. This is phi. This is V. Is it? That's all from this explanation. Okay. Now we will go to the core loss. How can be printed core loss? There is an equation, that is, see here, we have taken this phasor diagram. This is IE. Okay. This is IM, called magnetizing component of the no load current. This is called IC, called core loss component or working component of the no load current. This is phi, this is V. So whenever the current is in phase with V, there will be a active power. There will be a active power. As in the case of resistor, so see here, this is resistor I, this is V. So here the voltage is in phase with current. There will be P not equal to 0. Q always equal to 0. Here also, so V, the current IC, so core loss component is in phase with V. So there will be active power. That active power V dash IC is equal to PC. This is core loss component, core loss of the transformer at no load condition. So this component of current only supplies the magnetic flux. This component of current supplies the core loss of the transformer at no load conditions. Of course, it is at loaded condition also. This is all about hysteresis, the part of the hysteresis losses. Okay. From this, we will say that I1 is equal to IC bar plus IE bar. Is it? These two are I1 is equal to IEC bar plus IE bar. This is all phasor sum. Okay. I will draw the equivalent circuit for this no load condition. That is, so this is V1, applied voltage. Here I1 is sum of the core loss component and excitation component. This is actually, this excitation component is 90 degrees lagging to the voltage, so we can put J. Okay. Now this is the phasor diagram, circuit diagram at the no load condition. So this is IE, this is IC because resistance is represented. This is IM, this is XM, this is RC. This branch is fictitious branch, means we have modeled the core loss for this information. To analyze the transformer in an equivalent circuit, we have represented or we have modeled the core loss to this circuit. Okay, means this is imaginary circuit we have modeled. Okay, this is all about circuit at the no load condition. Now we will introduce the leakage impedance, means leakage reactance and the resistance of the winding. So usually for a transformer there is a winding resistance R1 present. R1 is directly proportional to length. So in fact the length of the winding is more. Even though the resistance per unit length is small, but entirely considering the length of the winding solenoid, will consider the resistance of the winding. Okay, this is all. So there is a resistance for the secondary winding also, that is called R2. Now coming to the leakage flux. What is leakage flux? Actually, in a practical transformer, all flux which are emitting from the coil 1 does not link to the coil 2. That is, all the flux that doesn't confine to the path of the core. Is it? That's why there is a leakage at the primary and the secondary. That flux is called leakage flux. So I will say this is primary winding, this is secondary winding. Okay, we have connected source V1 here and the flux will be emitted. So this flux is called core flux. Some part of the flux doesn't link to the secondary winding, means this links only primary winding. This is called phi L1. Of course, there is a leakage flux at the secondary also. So this is phi L2. So coming to this modeling, means we have to model this leakage flux to analyze the transformer. Okay, this is, so leakage MMF, can I write leakage MMF? Leakage MMF is equal to N1 into I1 or IL1, not. So leakage, linkages means flux linkages. I will write this in this way. Okay, leakage flux linkages is equal to lambda is equal to N1 into phi L1. Is it? This is equal to I1 into L1. I will put inductance for the small l. Okay, L1. Is it correct? In the case of inductor, we will write that E is equal to d by dt into lambda, that is equal to N into d phi by dt. The same voltage can be represented L into di by dt. Is it correct? So that is equal to d by dt of L into I. This is equal. Okay, that's why we have written this. Now, so L1 leakage inductance L1 is equal to N1 phi L1 divided by I1. So under steady state conditions or loaded conditions or under not transient conditions, so we will assume that this is always constant. So L1 is directly proportional to phi L1. So leakage flux we have modeled to inductance L. This is the primary modeling. We can write L2 is directly proportional to phi L2. So flux we have modeled to a inductor. This is called passive inductor L2. So now we can draw the equivalent circuit of the transformer. Is it? See, draw. First one, primary resistance. Second one, primary leakage inductance. Here is shunt branch parameter RC, XM, and secondary winding, or we can write, we did not refer to the values, so this is ideal transformer, this is secondary resistance and secondary leakage inductance. Here is a V1 applied, here R1, L1, okay, R2, L2, JX1, JX2, okay, this is RC, this is XM. This is entirely a ideal transformer. Ideal transformer. So N1 is to N2. Okay. This is load we have connected, if connected. So ZL. This is called V2 or load voltage. Here I2 will flows. Here I1 will flows. Here IE will flows. Here I2 dash will flows. This is equivalent circuit, exact equivalent circuit of the transformer. Or you can write this in this way also. I have it. This is exact equivalent circuit of the transformer. Coming to the phasor diagram. So first I will write the equations and then we will go to the phasor diagram. From this we will write V1 is equal to, is it? V1 is equal to V1 dash. I will write this as a, this node voltage are V1 dash. Okay, V1 dash plus I1 into R1 plus J into I1 into X1. Okay. Next E2 is equal to V2. So these are all the phasor voltage, phasor diagram, phasor additions or phasor arithmetic, plus I2 R2 plus J into I2 bar X2. Okay, this is equations. From these equations we will draw the phasor diagrams. Okay. So first one. Okay. So take phi as reference here also. This is phi. So this is G1. So on opposite side V1 is equal to minus A1. Okay. Next minus A1. This is IM. This is IC. So the phasor sum gives rise to IE. Next one, this is I2, this is V2. So the drop, resistance drop is in phase with I2. So I2, R2. So reactance drop is at the angle of 90 degrees. 90 degrees. So this is I2J X2. This is E2. See here, the V2 is not in phase with E2 because of this leakage impedance I2 Z2. See here, this because of this leakage impedance, this V2 is not in phase with E2. Okay, referring the I2 dash at the primary, I2 dash will phasor sum will add these two I2 dash and IE will get I1. This is all about phasor diagram of lagging load. Is it? This is lagging load. So for leading load, we'll get okay. See here. Here this is wrong. This is somewhat different. So this is V1 dash. To this we have to add leakage resistance and reactance. Then we will get V1 here. V1. So V1 dash here I have written the V1 dash plus I1 R1 plus J into I1 X1. So this V1 dash is equal to minus C1. So this is I1 R1. This is I1 X1 J. This is all about the phasor diagram of the lagging load transformer. If I write the leading load, then this phasor diagram will modify to this way. I will take only secondary circuit. This is V2. For leading load, I is leading in this way. So I2 R2 is in this way. This is I2 X2. This is E2. From this we will say that at leading condition V2 is greater than E2. This is power factor angle phi 2. Okay, this is delta. This is all about the transformer phasor diagram at leading condition. Now we will derive the voltage equation for the lagging load and for the leading load. Okay, what is voltage equation? Now, considering only lagging phasor diagram at the secondary side only, so first taken V2 is taken. V2. So lagging condition I2 is lagging in this way. This is I2 R2 drop. This is I2 X2 drop. This is E2. Okay. This is phi 2 or power factor angle. This is delta. Now we can derive the E2 equation in two ways. First I will go to lengthy way. This is all given in Bembra. Okay. First one is this way. I will extend the line of I2 and the line of I2 JX2. They will meet at 90 degrees. O A B C. Okay. Now coming to this, so this I2 R2 drop is projected in this way. Okay, this is I will taken as D. Okay. Now see, by seeing this figure, I will write that by Pythagoras theorem. See this triangle OAC. Is it this triangle OA and C? Outer triangle. Only see that. Can I write OC is equal to root of OA square plus AC square? Is it? Yes, correct. Now can I write C here? This is it. So this is entirely OD is equal to V2 cos phi 2. Is it? Now AB is equal to AB is equal to V2 sin phi 2. Yes, it's correct. Okay, now go in this way. OA is equal to OD plus DA. OA plus OD plus DA whole square plus AC is equal to AB plus BC whole square. This entirely can be split into AB plus BC. Now write the values. OD is equal to V2 cos phi 2, V2 cos phi 2 plus dA I2 R2 whole square plus this AB is equal to V2 sin phi 2, V2 sin phi 2 plus this BC I2 X2 whole square. So this is OC entirely is equal to E2. This is E2, finding some way of finding E2. There is another simple way of finding E2. That is, see here, extend the line of V2 here in the same way. This, okay, draw an arc of radius OC. This will touch us at E. Z. Draw a chord of at E to E and extend this chord until this line, means drawing E F BF. BF is in parallel with the O, this line, so V2 line. It is in parallel with the V2 line, is it? So this is at 90 degrees. Now this is phi 2, is it? This also phi 2. How this is phi 2? So see here, by seeing the triangle OA and this, I will mark this as G point. See here, OAG, this triangle. This triangle, the angle at G is equal to 90 minus theta 2 or 90 minus phi 2. Is it? Angle at G, this angle is 90 minus phi 2. This angle also 90 minus phi 2. 90 minus phi 2. Is it? So these lines are, these two lines are in parallel. So this angle is also 90 minus phi 2. So this is 90 degrees, this is 90 minus phi 2. This must be phi 2 to satisfy the 180 degrees inner angles of a triangle. This is all about. Though this is somewhat clumsy, so I will draw the new phasor new diagram. This is V2, V2, I2, I2 are to drop. So I2, X2, I2, R2. We have extended this line. This is 90 degrees line. We have taken this. Okay. This is I2, R2. This is phi 2. This is also phi 2. 0, O, C, O, A, B, C, D, E, F, G. So okay, now can I write this OD is equal to OE? Okay, this is E2. OD is equal to OE. Okay, now OD is equal to OA plus AB plus BD. Is it correct? See here. We have splitted this line into three parts, OA plus AB plus BD. Here OA is equal to V2, is it? Now AB is equal to I2 R2 cos phi 2. Now BD is equal to I2 X2 sin phi 2. Is it? This is opposite side for this angle, this triangle. This side is opposite to this angle. So that's why we have I2 X2 sin phi 2. So by writing this, okay, so E2 is equal to V2 OA plus AB I2 R2 cos phi 2 plus I2 X2 sin phi 2. This is simple and less laborious in calculation of E2. Okay, now we are going to introduce impedance reference, means how to refer the impedances. Earlier we have referred one value, but see here the equivalent circuit is referred to primary side or entirely to the secondary side. Yet we will say that we have notation in Bimra, we have different notations. I'll say that if Z2 is referred to the primary side, then it is called Z2 dash. If I2 is referred to the primary side, then it is called I2 dash. Okay. Similarly, V2 is referred to the primary side, V2 dash. If primary values are referred to secondary side, then they will called Z1 dash. Z1 is referred to the secondary side. Okay, I1 is referred to secondary side, I1 dash. In this way we will go to the notation. Okay. Now if Z2 is referred to say primary side, then we will say that Z2 dash is equal to N1 by N2 whole square into Z2. This is direct ratio. We will take K is equal to here N1 by N2, or you can take K is equal to N2 by N1, or anyway you stick to one notation. Okay. Now Z1 dash is equal to N2 by N1 whole square into Z1. So this is K square into Z2. This is 1 by K square into Z1. Okay. Here secondary impedance is referred to the primary side. Here primary impedance is referred to the secondary side. And similarly the current also. Current is referred to the primary. Okay. I2 dash is equal to, or I'll say I1 by I2 is equal to N2 by N1. So I1 I will write I1 is equal to N2 by N1 whole into I2. So I2 dash is equal to 1 by K into I2. Okay, this is all. The referring the values. So one important note is, if the impedance is given in this way, but if admittances are given, the notations entirely will take different situation. Means if he will mention the admittance or shunt branch parameters as Y0 at the primary, if you want to refer the secondary, what you will say? So we will say 1 by K square Z1. We will Y now 1 by Y1 dash is equal to 1 by K square Y1. So this is wrong. So this is Y1 dash is equal to K square into Y1. This is, so there is a reverse situation we will take for the admittances, and the direct situation takes it for the impedances. This is all about. So this is important note we have to remember. Okay. Coming to the problems, we have two problems. First one is, in the first problem, this note is highlighted here. So I will take just a minute. Okay, here in the first problem he has given a 20 kVA transformer, 50H, 2000 bar, 200 volts distribution transformer has leakage impedance of 0.42 plus J 0.52 ohms in the high voltage side. So this is transformer. So at the high voltage side he has given leakage impedance. So here leakage impedance is 0.42 plus J into 0.52. Next, and the 0.004 plus J into 0.05 ohms in the LV side. 0.004 plus J into 0.05. Okay, in LV winding. When seen at the LV side, we have Y naught. So shunt branch parameters are given here. This branch parameter, I will take this way. He has given 0.002 minus J into 0.015 mhos. Not ohm. Okay. Draw the equivalent circuit referred to primary side. Okay. So we have to draw the equivalent circuit referred to the primary side. So what he has given, N1 is 2000 ohms, 200 ohms, 2000 turns, 200 turns. So K is equal to N1 by N2 is equal to 10. So if you refer the secondary to primary, we will take direct ratio, that is 10 square J2 dash is equal to 10 square into 0.004 plus J into 0.05, that is equal to 4 plus J 0.4 plus J into 5. Next, here he has given admittance, so that is also taken. Y2 dash is equal to 10 square into 0. Not 10 square, we will divide the by 10 square. Okay, because it is admittance, so by 10 square 0.002 minus J into 0.015 ohms mhos. So this is, if you calculate the value and draw the equivalent circuit at the primary side. Okay, this is our first problem. And the second problem, there is a tricky, that is so here the data is given, it's a big problem. First A we will calculate and then we will do the second problem. So what are the values given? So it's a 10 kVA, yes, 10 kVA. Next 2500 by 250 volts transformer, phase transformer, has resistance. So R1 is given 4.8 ohms and R2 is given 0.048 ohms. X1 is given 11.2 ohms and X2 is given 0.112 ohms. Okay, In the first problem, we have asked that when the LV winding is connected to a load impedance of 5 plus J 3.5 ohms, calculate the terminal voltage. We have to find V2. Here, for calculating terminal voltage, he has given Z2, ZL. So now we will require I2 or IL. This must be required. Then here the values are given. So this primary values x1 and r1 must be referred to the secondary side. We will get the Z2, ZE2 leakage impedance. So now R1 dash is equal to, what is here, 10 is given. So we will divide by 10 square. 1 by 10 square 4.8 plus J into 0, J into 11.2. So here 0.048 will come plus J into 0.112 will come. This is referring values. R1 dash, Z1 dash I will write directly. Okay, Z1 dash. Now sum these two. So I will get 0. ZE2 is equal to 0.96 plus J into 0.224. 224 with ZE2. Now total Z is equal to ZL plus ZE2, that is equal to 0.096 plus J into 0.224 plus 5 plus J into 3.5 ohms. Can I write? So 5.096 plus J into 3.724. Now I2 is equal to E2 divided by Z total. That is equal. E2 is given 250 volts divided by 5.096 plus J into 3.724. So this is equal to, we have got the answer 250 divided by mod. What will be the answer for this? Yes, we will calculate this and calculate the power factor also. This angle will come, this angle theta, power factor will be cos theta. This is all. Okay, next one, taking B, section B. So here he has given the power factor and the rated current. So rated secondary current. What is rated secondary current? Rated secondary current is equal to secondary current is equal to 10 into 10 power of 3 divided by 250. What will be the answer? So this 100 into 10 divided by 25. So I will get 40 amps. Is it? Okay, power factor is given. Cos phi 2 is equal to 0.8. Sin phi 2 is equal to 0.6. Is it? So we have all the parameters. ZE2 is equal to 0.096 plus J into 0.224. Okay. Now using the equation, E2 is equal to V2 plus I2 R2 cos phi 2 plus I2 x2 sin phi 2. Substitute all the values except V2. We have to find the V2. So 250 is equal to I2. What is the I2? V2 plus 40 into 0.096 6 into 0.8 plus 40 into 0. Not it's a 0.224 into 0.6. So V2 is equal to, we'll find from this. Okay, this is all about the second lecture. Thank you for listening.